Hello, everybody. It's Miss Maneely, and I am going to go through the first quarter review packet in AP Statistics. So in the first question, you are given a back-to-back stem and leaf plot. It says, of the 50 species of oaks in the United States, 28 grow in the Atlantic coast and 11 grow in California. We are interested in the distribution of acorn volumes among oak species, and here are the back-to-back stem and leaf plots on the volumes of acorns. This is in cubic centimeters for the 39 oak species, or for these 39 oak species. And you're asked to compare the shape, center, and spread of the two distributions in context. So let's go ahead and first understand what the shape of these distributions are. It's difficult to tell because the number line is vertical instead of horizontal, but if you turn the graph, and I know you can't really do this on your paper, but if you just kind of turn your paper sideways so that the number line goes in the appropriate direction, so it goes from least to greatest, I think it's a little bit easier to see that the shape is going to be skewed to the right. And obviously, with the acorns on the Atlantic coast, if you were just to flip this upside down, I don't know if I can actually do that, but if you were to flip this upside down, you'd be able to see that the distribution of acorns on the Atlantic coast is also skewed to the right. When the tail is pointing to the higher numbers, that tells you that the distribution is skewed to the right. Okay, so let me turn that back around. Let's just get rid of that. All right, so we want to compare the shape, the center, and the spread. So we've already said the shape, and I'm just going to jot this stuff down. You're going to obviously want to write this in a paragraph form, but the shape for both is skewed to the right. And this is not how you're going to want to write it on your test. But let's go ahead and talk about how we would find the center and the spread. You can certainly enter the values into your calculator and do your 5-number summary that way, or compute your mean and your median that way. It might take a little bit of time, but let me show you how you would do that so that you're interpreting the stems correctly. So for example, this number here actually corresponds to 3, a volume of 3 cubic centimeters. And the next one would be 4, 6, 8, 9, and 9. The numbers here would be 11, and then 12, 14, and so forth. So the stem gives you the first 2 digits, and then the leaf gives you the 3rd digit. So you can certainly enter in all of the values in a list if you want. And then just list them all. Or, since I already know that 28 of the species are on the Atlantic coast, that tells me that the acorn that is between 14 and 15 would be the median. So if I simply count, and I start at my leaf when I count, so that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this position right here is going to correspond to the median of my distribution. And if I think that's between 16 and 18, so I can compute my median. It's going to be 17 because I would just average the two numbers between 16 and 18. If I want to compute the lower quartile, that tells me I have 14 digits below and 14 digits above. So that means that between the 7th and 8th position would be where my Q1 would fall. So if I count 1, 2, 3, 4, 5, 6, 7, then my 8th position right here is where my Q1 would be. And that tells me that my Q1 is going to be 11. My min would be this number here, is 3. And I can see my max is this number here, and that's going to correspond to 105. So the only other number I need to figure out would be my upper quartile. So again, if I count, there's 14 values above my median, so if I figure out where the 7th and 8th position are, that'll enable me to find my upper quartile. So I'm actually going to start from my max and work backwards. So this is obviously 1, 2, 3, 4, 5, 6. Actually, this would be 6, 7, and then my 8th position would be right there, and that would be between 34 and 36. So that gives me a Q3 of 35. And then I can do the same thing with my California acorns. This time I know that there are 11 values, so that means that the 6th value is going to be my median. So it's not going to be between 2 values, it's actually going to be a number in my data set. So again, I'm going to count from the stem over, so 1, 2, 3, 4, 5, So this is my sixth acorn, and that's going to be my median, because remember the stem and leaf plot, everything's already in order. So this is my median, and my median then would be 41. I know my min is right here at 4. I know my max is right here at 171. And so now when I compute my lower and upper quartiles, the median is not going to be included, but the min will. So I'm looking at if I've got 5 data values below my median, then that means the third value is going to be my lower quartile. So 1, 2, 3. That value right there means that my Q1 is 16. And if I go back 3, 1, 2, 3, that means my Q3 is 60. And so I now know my median for both. So my median for the Atlantic coast, let me just write this all down here so it's a little bit easier to see. The median for the Atlantic coast is 17. The median for California is 41. Since I'm dealing with skewed distribution, I can go ahead and compute the interquartile ranges as well. So the interquartile range for my Atlantic coast would be Q3 minus Q1, 35 minus 11, which would give me 24. And is that right? 35 minus 11. And the IQR for California would be Q3, which is 60, minus Q1, which is 16, and that's going to give me 44. Okay, so those are my summary statistics. So then when I'm going to compare the shape, the center, and the spread of the two distributions in context, I want to make sure that I'm comparing the shape. So I'm going to say that both distributions are skewed to the right. I need to say something about the center and the spread, and I want to do it in context. So I'm going to give you an example in just a second, but you want to make sure that you're referring to the context of the problem. So you might want to just start off and say the graphs to the right describe the distribution of volumes of acorns in the Atlantic coast and California regions. I can certainly say that the typical acorn in California is much larger than the typical acorn on the Atlantic coast. And then you want to actually put the median values in there as well. So it looks like it's more than twice the size of the Atlantic coast volumes, where the median for California is 41 centimeters cubed compared to the median on the Atlantic coast, which is only 17 centimeters cubed. So it's about twice, the acorns in California are about twice the size, at least, of the Atlantic coast volumes. In terms of the IQR, when you're talking about the context, you can refer to the consistency. So you might say something like it looks like there's an outlier in California. You'd actually want to check that, though, with your interquartile range rule. But you could certainly say that the interquartile range for California is actually much larger at 44 compared to the interquartile range for Atlantic coast acorns. Okay, and I actually have a sample response for you to read. You don't have to go into this much depth with the answer, but certainly you want to make sure that you're talking about the shape, the center, and the spread, and you're referring to the context of the problem. So I've written the stem plots show the distribution of acorn volumes on the Atlantic coast and in California. Both distributions are skewed to the right. So notice when I'm saying both distributions, that's a comparison. So both are similar in the sense that they are skewed to the right. So there's my shape. It says a typical California acorn has a much larger volume than those on the Atlantic coast. So there's my comparison there, with a median of 41 centimeters cubed, which is more than twice the volume of a typical Atlantic coast acorn of only 17. However, the Atlantic coast acorn volumes are much more consistent with an IQR of 24 cubic centimeters, which is much smaller than the California acorn's IQR of 44. So again, you've got the comparison, and I'm actually bringing the values of the of the center and spread into the description. Okay. In the next problem, you are given two box plots. And these represent the heights in centimeters of male and female students in a class. So you are given the box plots, which show your 5-number summary, and you're given some statements that you have to mark as either true or false. So the best thing to do here is just to read each statement and determine it's truth. So in the first one, it says about 50% of the male students have heights between 170 and 178. So 170, so this is my male, so 170 to 178 looks like it's about right here. So that looks like it is between Q1 and the median. And that's actually going to be 25% of the data, not 50% of the data. So that statement is false. The next statement says about 25% of the male students are taller than the tallest female student. So here's the tallest female student. And so what we're looking at is this distribution right here, or that part of the distribution. And that is also 25%. So that statement is true. We've got 25, basically our upper quartile for the males is equivalent to the max of the females, meaning that 25% of the males are going to be taller than the females. So that's true. The next one says the mean height of male students is about 178 centimeters. So 178 centimeters is right about here. That corresponds to the median. Remember, when you're given a 5-number summary or a box plot, it's the median, not the mean. So we can't know exactly what the mean height of males is. So this is actually a false statement. Now, even though we can't know exactly what it is, we can determine its relationship, the mean's relationship to the median based on the shape of the distribution. So if we take a look at the next statement, it says for female students, the mean height is greater than the median height. So in this case, this distribution is slightly skewed to the right because it's stretched to the right-hand side, and so that means that the mean height will be higher if it's skewed to the right. So the mean is greater than the median, and that is a true statement. Even though we can't see the distribution exactly, because it's slightly skewed to the right, I can tell that the mean is going to be higher than the median. The next statement says that there are fewer male students with heights above the median than below the median. Well, think about what the median means. It's the middle value. And if it's the middle value, then there are exactly the same number of students below it as there are above it. So even though the spread is different, so I can see that the spread above the median is smaller than the spread below the median, but that doesn't have anything to do with the number of students that fall in those spaces. So there's still half the data is less than the median, half is more. So this is a false statement. And then the last statement is that the 25th percentile for females is 160 centimeters tall. The 25th percentile is your first quartile, and so that is actually a true statement. All right. The next problem is very similar to the free response questions that I've asked you to do. We've done like 3 of them already, so I'm expecting each of you to get a perfect score here. You are given some information about values of gasoline additives, and you're asked to construct parallel box plots showing outliers. Then you're asked to compare the distributions and choose which additive would be better. So number 3 says, a consumer advocate conducted a test of 2 popular gasoline additives, A and B. There are claims that the use of either of the additives will increase gasoline mileage in cars. A random sample of 30 cars was selected. Each car was filled with gasoline, and the cars were run under the same driving conditions until the gas tanks were empty. The distance traveled was recorded for each car. Additive A was randomly assigned to 15 of the cars, and additive B was randomly assigned to the other 15 cars. The gas tank of each car was filled with gasoline and the assigned additive. The cars were again run under the same driving conditions until the tanks were empty. The distance traveled was recorded, and the difference in the distance with the additive minus the distance without the additive for each car was calculated. The following table summarizes the calculated differences. Note that the negative values indicate less distance traveled with the additive than without it. So this was an experiment. We've controlled all other factors. We're dealing with the same vehicles before and after the additive was placed in the tank, and they were all driven under the same driving conditions. And we're looking at the difference in mileage before and after the additive. So you're given the 5-number summary along with several other values. So what the information in this table doesn't give you all of the values in the distribution, and part of this is because you're asked in letter A to construct a box and whisker plot showing outliers. And the reason they didn't give you all of the data values is because they want you to show that you understand the outlier rule. So you're given the values that are below Q1, which would include the min. So here's your min. You're given Q1, the median, Q3, and then the values above Q3, which include the max. So you are given the 5-number summary in each of these distributions, and you're given just enough information to be able to determine whether or not there are any outliers. So let's think about our outlier rule. A low outlier would have to be less than Q1 minus 1.5 times the IQR. And a high outlier would have to be above Q3 plus 1.5 times the IQR. And so what we want to do is compute this for both distributions. So I'm going to do it for additive A right here. And I'm going to look. Are there any low outliers? A low outlier would have to be less than Q1, which in this case is 1, minus 1.5. And if I take a look at my IQR for additive A is 4 minus 1, or 3. And so if I compute that 1 minus 1.5 times 3, I get a negative 3.5. And so what I want to do is circle any values that are less than negative 3.5. Those are going to be outliers. So that tells me that my min is an outlier, and so is negative 8. Now I want to check to see if I have any high outliers. And so my high outliers, I start with Q3, so that's going to be 4 plus 1.5 times my interquartile range, which is 3. So I'm looking at 4 plus 1.5 times 3, which gives me 8.5. So I'm looking for any values that are greater than 8.5. And that leaves me with 1. That gives me 9. I want to do the same thing with additive B and see if I have any outliers in additive B. So again, I'm going to do the same thing. I'm going to look for low outliers first. My lower quartile is negative 2. I'm going to do minus 1.5 times my interquartile range is going to be 25 minus a negative 2. So don't forget that it's going to be minus a negative 2, which actually means that my IQR is 27. And when I multiply out, I get negative 42.5. And there's nothing below that number, so I don't have any low outliers for B. When it comes time to looking for the high outliers, I'm using Q3, which in this case is 25, plus 1.5 times 27. And that gives me a value of 65.5. And since my max is 40, I have no high outliers for additive B either. So now I want to go ahead and construct my box and whisker plots. This is something you have to do by hand because you don't have all the data values in order for the calculator to compute your 5-number summary. I found that the best way to scale my graph, since my minimum is negative 10 and the maximum for both distributions is 40, I went ahead and just scaled it. Like this was negative 10, and then I counted every 4. So this was 0, this is 10, this is 20, this is 30, and this is 40. Now you want to make sure when you're constructing box plots that you also give a title to your graph. And so in this case, this is going to be the difference in gas mileage, or the difference in mileage. All right. So when I am looking at additive A, I want to go ahead and first identify my outliers. And I'm going to use asterisks to identify my outliers. So I have an outlier at negative 10. And I have an outlier at negative 8. So halfway between 0 and negative 10 is going to be 5. If I go another mark, that's going to be 3/4. So negative 8 is going to be like right about there. And if it does help me when I'm grading, if you actually write the numbers above each of the places on your box and whisker plot. So negative 2 now is going to be the next space, and so that's going to be like here. And then my lower quartile is 1. And so between 0 and 10, this is maybe right here. So I'm going to put a 1 there, a negative 2 there. My median is 3. So let's see, 2.5. There's 3. I'm going to start my box. And then it's going to go to 4. And then, so let's see, we got this. Oops. Let me start that over again. Okay, I'm just going to put dots on everything, and then I'll connect everything in just a second. So my Q3 is actually going to be 4, which is a little bit less than halfway. And then I've got a high outlier at 9, which is going to be about right here. And then I need to show where 7 is going to be, which is about right here. So I'm going to connect these two as whiskers. And then my box is going to go in here. And so my median was 3. This is 4. This is 7, and this is 9. Okay, and this is for additive A. Okay, so for additive B, I don't have any outliers, so this is actually going to be a little bit easier to plot. So -5 is my minimum, so that's right here. And then -2, which is going to be about right here. 1, and then 25 is my upper quartile, and 40 is my max. Okay, and then I'm also going to label everything. So this is -5, this is -2, -1. I'm sorry, not -1, +1. This is 25, this is 40, and this is my graph for additive B. Okay, so I've labeled everything, I've drawn my graph, my scale is consistent. The next thing I want to do is to compare the two gasoline additives. So let me just talk it out, and then I'm going to give you a sample response in just a second. So when we're talking about the context, the first thing you might want to say is the graphs above, or the box plots above, show the distribution and the difference of gas mileage with additives A and B. I can definitely see that additive B is much more skewed to the right than additive A, which is a little bit more symmetric. When I'm comparing the typical mileage, there is a difference, but it's a very small difference. So additive A is only 2 miles greater than additive B, with a median of 3 compared to a median of 1 for additive B. But the ranges and the interquartile range of the two distributions is very, very different. Additive B has a much larger spread. It's much less consistent. And sometimes consistency, sometimes a lower consistency is a good thing. But in this case, I think the having less consistency is a good thing in this case, because I think additive B actually shows that you're going to get more miles out of the gas than additive A. And so in letter C, when it says which additive would you recommend to increase the gas mileage, I think it's pretty obvious that additive B would be better. And then there's lots of ways that you can justify your choice. You want to make sure, though, in letter B that you're comparing the center and the spread. You can certainly talk about the maxes and the mins, but that doesn't really go toward describing the center and the spread. Those would be the evidence that I would share in the last statement. So if I'm trying to justify that additive B is better, I might say because the max is 30 miles bigger than the max for additive A. I could also say something like 25% of the cars got more than 25 extra miles per tank, which is a good thing. So let me give you some sample responses. Okay, so in comparing the gasoline additive, sorry, the box plots disappeared, but the box plots show the difference in miles driven with additives A and B. The distribution of miles for additive B is much more skewed to the right than additive A, which is quite symmetric. The typical difference in mileage is similar. Typically, cars with additive A traveled an additional 3 miles, which is only slightly larger than the typical increase of mileage with additive B, which is only 1 mile. The spreads of the distributions are quite different, though. The mileage for additive A was consistently much less than for additive B. The range for additive A, which was 19 miles, was less than half of that of additive A, which was 45 miles. So when you're asked which additive would you recommend to increase gas mileage, I would recommend additive B, since 25% of the cars got at least 25 additional miles. Also with additive A, there's a risk that you could actually decrease mileage by 10 miles. And obviously answers are going to vary here. and your conclusion about which additive is better could be a little bit different than mine, but you just need to make sure that your justification is reasonable. Okay, number 4. This gets into chapter 2 now. It says, Miss Morgan administered a test to her class and found that the average score was 72% with a standard deviation of 8%. Lily earned 78 on the test, and you're asked to calculate her z-score. So remember, a z-score is determined by taking the observation minus the mean over the standard deviation. So for Lily, she scored 78 on the test, which was above average. So I'm going to subtract the 72 and divide by 8. And when I do that, I get 0.75. That has to do with the number of standard deviations she is above the mean. So in letter B, it says, Miss Morgan decided to curve the test scores using the following rule. She's going to take 1.5 times the old score and subtract 25 points. Determine the new mean and standard deviation for the transformed test scores. So if I want to find the new mean, I'm going to be able to perform both operations. Notice that I'm multiplying by 1.5 and subtracting 25. And when I'm transforming data, both of those operations are going to impact the mean. So all I'm going to do is take 1.5 times my old mean, which was 72, and subtract 25. And when I do that, I get 83. The new standard deviation, however, I need to be careful. I'm still going to go ahead and multiply by 1.5, but subtracting the 25 from all the scores is not going to change how far apart they are. So I'm not going to subtract 25 when I'm computing the new standard deviation. The new standard deviation is just going to be 12. And we're given units here. These are percentages. And you don't have to change it to decimals. You can just use the percentage as the unit. In letter C, it says, according to the rule, what would Lily's new test score be? So basically, I'm going to take Lily's old score. So her new score is going to be 1.5 times her old score. And we said her old score was 78 minus 25. And so when I compute that, I get 92. And then in letter D, it says to compute her new z-score based on the transformed test results. So now I'm going to use this as my x, this as my mu, and this is my standard deviation. And I'm going to see what happens to her z-score. So her new z-score is going to be 92 minus 83 over 12. And when I do that, I get 0.75 again. And so the idea here is that no matter how I transformed the results, her score is still 0.75 standard deviations above the mean. So even if I was to divide them in half or add 65 points, any changes I make to the data itself is not going to change Lily's position in the class in terms of her test score. So no matter how I transform the data, her z-score is going to be the same because no matter what, she's 0.75 standard deviations above the mean. Okay, in number 5, it says the Program for International Student Assessment, PISA, I guess, conducts tests in mathematics in countries throughout the world. For 15-year-olds in all developed countries, the scores in 2012 were normally distributed with a mean of 494 and a standard deviation of 92. A student in France has a z-score of 2.1. A student from the US has a percentile rank of 97. And a student from Spain scored 708 on the test. What we'd like to do is rank the students in order from lowest performance to highest performance on the PISA assessment. I think the easiest thing to do here would just be to convert everything to a z-score. I mean, you could do this a bunch of different ways. You could either convert everybody to a z-score, convert everybody to a percentile rank, or convert everything to the actual test score. So as long as you're consistent and converting everything in the same way, it's not going to matter which direction you go. I just think the z-score is the easiest thing. So in France, we already have a z-score. The French student already has a z-score of 2.1. So in the USA, I'm given a percentile rank. So if I'm given the percentile, I've got to really think about this distribution. This student ranks at the 97th percentile. That means that 97% of students scored below the student in the United States. I want to figure out the z-score associated with that. And so if I use my inverse normal, since I'm given the area under the curve, I'm going to use my inverse normal command. I'm going to put in the 97 because it's always the area to the left. I'm going to keep my mean and standard deviation at 0 and 1 so that I'm converting to a z-score. And that gives me a z-score of 1.881. Okay, and so I can see that the student in the United States did not score as high as the student in France. Let's go ahead and take a look at the Spanish student. We can see that the student in Spain earned a score of 708. That would be like an X value. So we know that the student in Spain earned a 708. What I want to do is convert that to a z-score. And so again, I'm going to use my formula, x minus the mean over the standard deviation. So 708 minus the mean, which we know is 494. And I'm going to divide that by the standard deviation, which is 92. And I will get 2.33. So now I've got z-scores for each student, and I can rank them. We want to go from lowest performance to highest performance. So the lowest performance was the student from the USA. The next to the highest was the French student, and the highest scoring student was from Spain. And like I said, you could also convert everything to X values. You could look at the percentile for each one. I just think it's easiest to compute the z-score for each student. All right, and number 6, this is another problem dealing with a normal distribution. A study of elite distance runners found a mean body weight of 63.1 kilograms with a standard deviation of 4.8 kilograms. Assuming that the distribution of weights is approximately normal, make an accurate sketch of the weight distribution with the horizontal axis marked in kilograms. So I know if I have a normal distribution, my mean is going to be in the middle, so 63.1. And then I'm just going to use my calculator to scale the rest of the axis, and I'm going to scale it according to my standard deviation. So I'm going to subtract 4.8, and we get 58.3. I'm going to subtract 4.8 again, and I get 53.5. Subtract again, and we get 48.7. And then on the other side, I want to add. So I'm going to take my 63.1, and I'll add my 4.8, and we get 67.9. I'm going to add it again, and I get 72.7. Add it one more time, and I get 77.5. And this is kilograms. Okay. In letter B, it says use the 68, 95, 99.7 rule, that's your empirical rule, to determine the proportion of runners whose body weight is between 48.7, so that's here, between here, and 67.9 in here. It says to shade the region under the curve that corresponds to this proportion. So I'm looking at this area here. And we're asked to use the 68, 95, 99.7 rule to determine the proportion. So there are lots of different ways that you can figure this out. The way I did it is I thought, okay, well, if I look at these two values, I know 68% of my data is right in here. I know if 68% is in the middle, then 32% is going to be in both tails. So the lower tail, all the way down, is going to be 16%. But I don't want all 16% because I'm not including anything below that. So I need to subtract that away. And if I think about it, that's going to be between, here, let me actually change colors. So this is 3 standard deviations below. This would be 3 standard deviations above. I know that's 99.7% of my data. That means 0.3% is going to be on the tails, or 0.15% below. And so I want to subtract that away. So what I'm looking at here is 0.68 plus 0.16 minus 0.0015. And that's going to give me 0.8385. There are lots of other ways that you could compute this, and if you want to just test it, you should end up with 83.85%. If you wanted to check to make sure that you're in the close range, now you're asked to use the empirical rule here. and not your calculator, but if you did want to just double check to make sure that at least you're in the right ballpark, if you go to your distribution menu to normal CDF, my lower bound would be 48.7. My upper bound would be 67.9. And in this case, I'm just going to go ahead because I'm not actually being asked to compute the proportion from the formula. I'm just going to go ahead and put in my mean of 63.1 and standard deviation of 4.8. And this is just so I can check my calculation to make sure that I'm in the right ballpark. And so the actual value is about 83.99. So I'm very close. That's a good way to reassure me that I've done this correctly. Letters C and D, you actually need to use your calculator because in letter C it's saying what proportion of runners have body weights below 60 kilograms. Well, 60 is not marked as one of the standard deviations away from the mean, so I have to use my calculator to do this. And remember, with these problems, you need to make sure that you're using appropriate notation. So if I'm letting X represent the weight in kilograms, always define your variable. I'm looking for the proportion of values then that are below 60. I also need to compute my z-score. And so I know it's an extra step, but on these free response questions, you need to make sure that you're doing it correctly. So I'm going to take 60 minus my mean of 63.1, and then I'm going to divide by my standard deviation of 4.8. And we get negative 0.6458. And so now when I go to my distribution menu, since it's a less than problem, again, never use normal PDF. We're always choosing normal CDF. My lower bound, since it's a less than, is going to be negative infinity. So negative 9999999. You can still use the X value if you want. So I can still put a 60 in here. And if I do that, I'm going to keep my mean at 63.1 and my standard deviation at 4.8. And I get 0.2592. I could have done the same thing. Oops. Sorry. Let's go back. If I could do the same thing, normal CDF, keep my lower bound at negative infinity, keep my upper bound at negative 0.6458. That's a z-score. If I'm going to use my z-values, then I need to change my mean to 0 and my standard deviation to 1. So you just want to make sure you're being consistent. If I do it this way, I should get the same thing. Now, I rounded my z-value, so my proportion is slightly different than the last one, but that's only because I rounded the z-value. So in letter D, we're looking at the proportion of runners that have body weights above 70. So I'm looking at X being greater than 70. I'm going to need to find my z-score. So we're looking at 70 minus 63.1 divided by 4.8. And I get 1.4375. And now when I go to find my area, this time since it's greater than, my lower bound is going to be 1.4375. And my upper bound now is going to be a positive infinity. And notice since I'm dealing with my z's, my mean is 0, my standard deviation is 1. And we get about 7.5%. Okay. All right, so that's pretty much it with Chapter 2. The last couple of questions deal with what we've been dealing with most recently in Chapter 3 and looking at relationships in bivariate data. So number 7, you're given a scatter plot. It says below is a scatter plot relating systolic blood pressure and age for 14 men from 42 to 67 years old. Is there a clear explanatory variable and response variable in this setting? If so, tell which is which. If not, explain why not. So I think it makes sense that there is an explanatory response situation here. I think we can see that as men get older, their blood pressure increases. So that means that my explanatory variable would be age. and the response would be the systolic blood pressure. Okay, it says to describe the association between the variables in terms of the strength, direction, and form. I think we can see as men age, their blood pressure increases. I'm just going to abbreviate that. I think there is a moderate, oops, positive association between the variables. And I think in terms of the form, we can say that it is linear. I think it's obvious we have an outlier. But if you think about whether it's linear versus nonlinear, there's definitely not a curve. I don't see a curve. When I'm thinking about the majority of the points, I can see there's a clear linear trend here. Yes, there's an outlier up there, but all of the other point values are in a linear pattern. There's not a curve. In letter C, it says, which of the following is closest to the correlation between systolic blood pressure and age for this group of 14 men? One thing I just want to remind you is that an outlier is going to have a significant impact on standard deviation. And since standard deviation, if you think about how we are computing the correlation coefficient, we're standardizing all the x values, we're standardizing all the y values. So the correlation coefficient itself involves the standard deviation for both x and y. So if we have an outlier, and this is an outlier not just with the x values, but with the y values as well, that's going to have a big impact on my correlation coefficient. My correlation coefficient is going to be very sensitive to outliers. So while I've got this nice, what looks like a very strong trend here, this outlier is actually going to have a significant impact on my correlation coefficient, and it's going to make it much smaller than it would be if that outlier was no longer there. So the correlation coefficient is likely much closer to 0.5 than it would be to 0.9. And so in letter D, so let's see, we'll just say the outlier has an impact on correlation, making it much smaller than it would be, making it weaker. And let's actually say closer to 0. Okay. That way we're being specific. Because sometimes when you say, the correlation is strong or weak, when we're describing the correlation coefficient, like if it's a negative association and you say that, the correlation is going to get higher, you really mean that it's getting closer to -1, which doesn't make a lot of sense because if you're going in the negative direction, you're actually getting lower. So sometimes it's just easier to describe what is happening to the R value. And in this case, the outlier is going to cause R to approach 0. In letter D, it says there's one unusual point on the graph. I've circled it. Explain what is unusual about this subject and what effect would removing the unusual point have on the correlation. Justify your answer. So here is a young man. So the outlier refers to a younger man with a very, very unusually high blood pressure. Removing him would strengthen the correlation and cause R to approach +1. Okay. In letter E, it says, suppose we rescaled the ages so that they were expressed as number of years above or below 50 years old. That is, suppose we subtract 50 from each value. Would the correlation change? Well, remember, the correlation is calculated from standardizing all the x values and standardizing all the r values, or all the y values. And if you think about one of those first questions we did with the test scores, let's see, Morgan's test score, or the class test scores, when we transform data sets, it doesn't change the standard value. It doesn't change the z-score. And since the z-scores are involved in computing the correlation coefficient, it's not going to change the correlation coefficient either. So my correlation is not going to change. The strength of the relationship is going to stay the same. So the correlation would not be affected by transformations in the data set. The relationship between the variables is going to stay the same. All right. So I think number 8 is the last one. And number 8 refers to several different problems on your quarterly assessment. So it reviews a lot of different skills related to least squares regression. So number 8, it says one characteristic of roller coasters that contributes to the maximum speed of the ride is the track's maximum height. Computer output is shown below for least squares regression of maximum speed in miles per hour on maximum height for 9 roller coasters that opened recently around the world. It says in letter A to write the least squares regression equation and being sure to define all variables. So we're told the variables in the problem. So it says we've got maximum speed and maximum height. And if I look at my output, remember when we're coming up with our least squares regression equation, we're interested in the 2 numbers that fall below the word coefficient. The number next to the word constant is going to be our y-intercept. So our y-intercept is 28.174, and my slope is going to be the other number, 0.21435 times x. And x in this case is going to be the height. So the height is the explanatory variable, and the response is going to be the predicted speed, or the maximum speed. Okay. It says to interpret the slope of the regression equation. So remember, the slope is always as the x value increases by 1, the y value is changing with respect to the slope. So I would say for every, or well, let's do it this way. As the height of a roller coaster increases, let's do it that way. Increases by 1 foot, the maximum speed, and be careful here, is expected to increase by 0.214 miles per hour. Okay, and letter C, it says to determine the correlation coefficient and then to describe what this value tells you about the relationship between the variables. So the correlation coefficient I can calculate by taking the square root of r squared. But I got to remember with r squared, that's written as a percentage, so I have to change it to a decimal. So I'm taking the square root of 0.613. I do want to do a quick check, though, of my slope to make sure that my correlation coefficient and my slope are the same sign. And since my slope is positive, my correlation coefficient is going to be positive. And when I take the square root of that, I get 0.7829. Okay, now I can't see a scatter plot of the data, so I can't really say for sure if it's a linear association. What I can say is there is a relatively strong or moderate, I'll say moderately strong, positive association between roller coaster height and its maximum speed. Oops. There shouldn't be an apostrophe there, sorry. Okay. And then it says to interpret the values of s and r squared. So let's go ahead and do r squared first. So we know that r squared is equal to 61.3%. And that tells me that 61.3% of the variation in the y variable, in this case the y variable would be in the maximum speed, can be determined by or explained by the regression equation on roller coaster height. Okay. S, this number right here, corresponds to my average prediction error. So S is our standard deviation of the residuals. And I'm going to actually just do this up here. So our expected, the expected prediction error is 10.5, let's just say 5.4. And this is going to correspond to my y values because we're talking about the residuals. So we're talking about miles per hour. So on average, and this might be a better way to say it, on average, my equation is going to be off in its predictions by about 10.5 miles per hour. And it's up to you to conclude whether or not that's too big or too small. It's hard to tell when you don't have a scatter plot. I believe in the next section you'll see the residual plot, and so that'll help you draw some more conclusions. In letter E, it says the Dominator at King's Dominion is a 161-foot roller coaster with a maximum speed of 65 miles per hour. It says to determine the residual for this coaster. So let's think about what a residual is. A residual is a deviation. And whenever we're computing a deviation, we always take our actual minus what we observe or what we expect. And let me actually write, I'm sorry. Actual minus the expected is what I want to write here, or predicted. Okay. So the residual here, I don't know. That's what we're asked to figure out. The actual speed, and the residuals are in reference to the y values. The actual speed we're told is 65 miles per hour. So what I need to figure out is what the expected or the predicted speed would be if a roller coaster is 161 feet tall. So to do that, I'm going to plug in my equation, 28.174 plus my slope 0.21435 times the height of this thing, which is 161 feet. And that will give me my predicted speed. So the predicted speed would be 62.684. And the residual, I'm just going to subtract 65 minus my previous answer. And I get 2.316. And that would be my difference. Okay? And that would be in miles per hour. And obviously this is going to be an underestimate. It doesn't ask you to write that, but I just wanted to reinforce that. Okay, and then the last part of this problem refers to a residual plot. So this is the residual plot for the roller coaster's least squares regression equation. So in letter F, it says to use the residual plot to comment on the appropriateness of the least squares regression equation. I think we can see that there's a random scatter of points. Above and below the regression line. There's no pattern, there's no curve, so that's a good sign. And I think we can also see that the predictions are all within, it looks like about 15 miles per hour. So all of my residuals are relatively small. Now, you could say that they are relatively large, and so therefore the model is not a good fit. But I think in this case, it's appropriate either way. The residuals are relatively small, being no more than 15 miles per hour off. And then just conclude, so the model is appropriate. If you think that being 15 miles per hour off is too big, then you'd conclude that the model is not appropriate. So this is where the judgment comes in. And as long as you back it up with a reasonable argument, I'm not going to mark you wrong. In letter G, it says the circled point represents a roller coaster in the Philippines whose maximum height is 70 feet. So this maximum height of 70 feet is an X value. It says to use the regression equation to predict the maximum speed for the roller coaster in the Philippines. So basically what I want to do is figure out my prediction. So I'm going to use my equation again. In fact, I'm going to hit second enter to actually call up my equation. And instead of having the 161, I'm going to type in the 70. And that gives me a predicted speed of 43.1785. And that would be in miles per hour. So that's the prediction. And then the last bullet says to use the residual plot and the previous answer to estimate the actual speed. So we're not given the actual speed this time. So again, think about your formula for a residual. It's residual equals the actual minus the predicted or expected. All right, well, I have the predicted, 43.1785. I'm trying to find the actual. That means that I should be able to figure out or estimate the residual. So if I go back up to my residual plot and look at this point here and I kind of come over to my axis, it looks like the residual for that value is 11 or 12. I mean, obviously, we might say it's a different number. It's just an estimate. So make sure you show all your work. So if I want to estimate what the actual value is, I'm going to need to add the 43.1785 to both sides. And so if I just add 11 to that number, I get an estimate that tells me that the actual speed is going to be approximately 54.1785 miles per hour. Okay, so I think if you understand how to do all the problems on this review packet, I think you are going to be golden on the quarterly assessment. I think it is a very, very fair assessment. There's nothing on the test that is not on this review in some way, shape, or form. So if you are able to answer the questions and you understand how to respond to each question and you understand how to interpret the values, then you are in really good shape. Other things that I would consider would be to go through your AP drills with the multiple choice questions to make sure that you remember the way some of the questions are worded, to double check the rest of your tests, see if there are any areas on the test that you still are confused about. But honestly, I think the review packet is going to be your best bet. So I wish you guys the best of luck. I think you're going to do great on this test. I really do think it's a fair assessment, and I have lots of hope for you guys. Good luck.